All right, let's continue looking at some examples of limits. So more limit examples. Look at two specific types of limits here. So for our first one, let's look at some infinite behavior with limits. And I know we've explored infinite behavior before, but let's do another example. So what if I were looking for the limit of this rational expression, x squared plus 6x plus 8 over x minus 3? Now, using what we've been doing with the direct substitution or the replacement, we would start with just trying out some direct substitution. So what happens when we try direct substitution? What happens when we do that? Let's see. So we do direct substitution and we get 9 plus 18 plus 8 over 0. Of course, that's interesting. I will make that red. Interesting, and also a problem for us in terms of computation. Can't divide by 0, but what is the top? So we end up with, what do we end up with here? 35 over 0. So what does that mean to us? So something like 35 over 0, right? We always have to pause for a second after we do our little direct substitution. That's always our start. And we pause for a second and we think, what can that mean for me, right? It means something. It's not my answer. 35 divided by 0 is not an acceptable answer. Obviously, division by 0 is undefined. So what does it mean? It means we need to do something more. But if I were to take 35, remember we're trying direct substitution to see if that works and gives us back the function value for the limit of this function. And we don't. The function itself does not have a value here. The function would be undefined at 3. But what about the limit? What's the behavior of the function around x equals 3? And this gives us a clue. So the clue that we have right here is that because the numerator's it's a positive whole number, 35, doesn't matter if it's whole number or not, it's a finite number, and it's not 0. If we've got something of that nature, like 35, and we're dividing by something that's approaching 0, right? Remember, not right at 3, the denominator is 0, but as we get close to 3, it would just be approaching 0. So if we're dividing by something that approaches 0, that means it gets very, very small. So if we divide by something that gets very, very small, we are going to have some infinite behavior. So if we have some sort of infinite behavior, we have to think about the fact that is it growing without bound or decreasing without bound? Is it approaching or going towards a positive infinity or a negative infinity? So we have some sort of infinite behavior. Now we just need to find out if that infinite behavior would be positive infinity or negative infinity. So all of this is sort of my thought bubble, right? As I'm going through, I do that direct substitution and I think to myself, okay, what am I going to do now? Because now I have to do a little bit more work, right? Anytime we've got a division by 0 or a 0 over 0, something that we can't just definitively say that is this value, this limiting value. Anytime I come across something like that, I have to use that information. It's like a piece of the puzzle. I use that information to go back and then actually compute the limit using some techniques that we've built up. So that's exactly what we're going to do here. We're going to come back to our limit now. We know we've got some kind of infinite behavior. And so we're going to come back to our limit and we're going to say, okay, let's figure out what this limit is if it exists. Now, notice we are approaching 3. It is non-directional. Okay? Since this is a non-directional limit, we must consider both sides. So a non-directional limit means we must consider both sides of 3. We must look at x approaching 3 from the left and x approaching 3 from the right. So in order to compute this limit, in order to determine if this limit exists, since it's a non-directional limit, we have to consider both cases. Now, if that x approaching 3 had a direction on it, if it had that from the left or from the right given, then we would go just to that one side and consider that side. But we actually have to look at both sides. So let's look at both sides. So let's consider the left first. So as we are approaching 3 from the left, what is going to happen to x squared plus 6x plus 8 over x minus 3? Now, I don't know that this matters or not, but I do notice that on this one that the numerator factors. I don't know that that's going to help me. It's not going to have a common factor with the denominator, but it might help us in simplification and computation. So let's go ahead and just factor it. X plus 4, x plus 2, x minus 3. Okay, so as I'm looking at that, I can see that as I approach 3 from the left, so again, kind of thinking about what does approaching 3 from the left mean? So approaching 3 from the left side, that means that we're plugging in, my little thought bubble again, plugging in values like, this is what's going on in my head, like x equals, we're coming from the left of 3, so 2.999, something like that. That's the values that I'm plugging in, okay? So that's the values I'm thinking about as I'm doing this computation. That means I'm approaching 3. In the numerator, I can actually use direct substitution. In the numerator, as I approach 3 from the left, x plus 4 is going to approach 7, and x plus 2 is going to approach 3 plus 2, 5. So in the numerator, I'm actually going to get that 35, just like we had with the direct substitution. So I don't know that it mattered that we factored or not, but we did, so we've got it factored. As I approach 3 from the left, x minus 3. So again, if it helps you, actually think of a numeric value that you would be putting in if we were still using tables. Something like 2.999999999 if you want to, or 2.9 or 2.99. Something to give you, something like that you can hold on to and actually think about. So if we plug that in there, 2.999 minus 3 is going to give me a value that gets very small, approaches 0, but does so from the left, right? It's approaching 0. If I take 2.99 and I subtract 3, I get something like negative 0.001, okay? Which is approaching 0. It's getting small, but it's doing so in a negative way. So remember what this means, right? We're going to write the mathematical form here, 0 from the left, but this means that we're plugging in a very small negative number. That's what that means, right? This is a very small negative number. It is approaching 0 from the left. So we end up over here with 35 divided by something that's approaching 0 in a negative way, right? That's approaching 0 from the left. It is negative. So when I take 35 and I divide by this very, very tiny negative number, this limit, this function to the left of 3 is going to be approaching a negative infinity. It's going to, this quantity, the magnitude of this division is going to be approaching, it's going to be decreasing without bound because the sign of it is going to be negative and it's going to be getting in size very, very large. So we classify that as negative infinity. So notice that we have negative infinity from the left. So this was our left-hand computation. Now let's do the same thing, but let's go from the right. And this is going to look very similar actually. So as we go from the right, our calculation, the right-hand limit here, our notation is going to look similar. We're coming from the right though this time, so we put that direction on the limit of x squared plus 6x plus 8 over x minus 3. And of course we can go back to that factored form, and I'm trying to go a little bit faster here because the computation looks real similar here. The numerator is going to also look similar when I do this computation, except this time, again, my thought bubble here, I am actually plugging in values this time to the right of 3. So I'm plugging in values like, right, if we come from the right side of 3, those are values like x equals 3.001. So that's, if it helps, sometimes it does. Sometimes it actually helps to have a number. So I like to put that thought bubble there. So then we are going to be approaching, of course, in the numerators, we plug in values for x that are approaching as we approach 3 from the right as x gets infinitely close, arbitrarily close to 3. The numerator is going to approach 7 times 5, just looking at the factored form, or you could go back and plug in 3 to the original expanded polynomial there. That is going to be 35. And in the denominator, denominator, we are approaching 0, but this time we're approaching 0 from the right, or positive values that get very, very small. So these are, notice what that notation means. These mean very small, but coming from the right side of 3, these are very small positive as I plug those in, positive numbers. Okay? Very small positive numbers. They get smaller and smaller, in fact, infinitely small. And so what ends up happening is we still have that 35, but this time we're dividing by something that is approaching 0 from the right side, meaning it gets very small, but in a positive way. Okay? When that happens, when you take 35 and you divide by a very tiny number, you are going to grow without bound, which means our value there is infinity. Okay. So what does all that mean about my limit, right? We've now looked at the left-hand side, we've looked at the right-hand side, and what we have shown here is that the left and the right do not equal each other. The left and the right side of this particular value, x equals 3, are not approaching the same value, or they're not both growing without bound, or they're not both decreasing without bound. What that means for us actually is that this limit does not exist. The limit doesn't exist because from the left side, the values decrease without bound. From the right side, they increase without bound. If we were to think about what that means, right? If we're from the left side, we're decreasing without bound. Here's 3. Decreasing without bound. From the right side, we're increasing without bound. We've got something that looks like this. This is, of course, x equals 3. This is a vertical asymptote for this particular function. And I've just done a very rough sketch. Who knows what it looks like elsewhere? We'd have to get into some more details on graphing for that. But this is the rough sketch of what's happening. The left doesn't equal the right, so my answer here when I have infinite behavior like this, and it's not directional, right? If all I had been asked to give was the limit as we approach 3 from the left or 3 from the right, we do have values. We've just calculated that from the left we're approaching negative infinity, and from the right we're approaching positive infinity. I shouldn't say we have values. We have behavior we can capture. We can capture growth or decrease without bound. But when we're looking at the non-directional limit, we have to actually answer in this way. We have to say that the limit of this function, x squared plus 6x plus 8 over x minus 3, as x is just approaching 3, non-directional, we have to actually say dne. Remember, dne does not exist. And also remember that anytime we have doesn't exist, we need to justify why. And so what we can say here is, we've justified it in the lines above, but what we could say right here is because the left-hand limit does not equal the right-hand limit. And that is my shorthand notation. We've showed the justification. This is our answer. Our final answer is that it doesn't exist. And we've showed the justification up above that the left-hand limit does not equal the right-hand limit. Okay. So let's leave that all on one screen here, maybe make it just a little bit bigger. But that is a really nice example of some infinite behavior, proper notation to show what that infinite behavior is on both sides of a value. And when we do have a non-directional limit, we do need to consider both sides in order to make the conclusion here. All right, let's do one more example in this video. And so let's explore a piecewise function. So suppose I had this function, f of x equals the absolute value of 2x over x. And at first glance, that might not seem like an actual piecewise function to you, but absolute value is a piecewise function. And we'll talk about that and break this down into its pieces. But what if we wanted to, with this function, we wanted to find the limit of the absolute value of 2x over x as x is approaching 0. Okay? So what if that's the limit that we actually wanted? Now, let me say this. Try direct substitution, just like we always, give an attempt to direct substitution. And let's see what happens. We try direct substitution, plugging in 0, and notice what occurs. The absolute value of 0, of course, is 0. So we end up with this 0 over 0. And remember that that means for us that we need to do more work, that there's something interesting. Obviously, the function itself, not defined at 0 because of the division by 0. We're not so much concerned, though, when we look at limits, whether the function exists. if the function does exist at that point, then the limit will be equal to the function's value if we can take the, or it could be equal to the function's value if we can take the limit. But in this case, this is going to mean does do more work, right? Even though the function is undefined at 0, that doesn't necessarily mean that the limit doesn't exist or is, it just means we need to do more work. It means we don't know, right? That's all it means. Okay, so let's go ahead and talk about how could I actually write this function as a piecewise function. I mentioned when we first started this example that this is in fact a piecewise function, but it's not written in its pieces yet. It's written in its absolute value. So how would we write it as its pieces across a broken domain? So let's talk about that. So first of all, let me come over here and let's just talk about absolute value for a second. So side note here, review on absolute value. Absolute value is defined in pieces. The absolute value of A, and I just use A to mean anything. It doesn't matter if this is an expression or a number. The absolute value of anything, of some quantity A, is actually 2 pieces. It's equal to A if that quantity is greater than or equal to 0, and it's equal to the opposite of A if A is less than 0. So just why is that? How does that work? Well, let's just think about it, right? If we took the absolute value of 7, of course that's 7, but if we took the absolute value of -7, it's actually the opposite of -7 or +7. Okay, let's write that one more way. -7, which is 7. Okay. So that is how we can break down absolute value into pieces, and that's what we're going to do. I used A to stand for anything. In our particular case, we've got this 2x that we're working with. So we've got this absolute value of 2x. So if we're talking about the absolute value of just 2x, I'll throw the x on it in just a second. If we have the absolute value of 2x, that's going to break down into 2 pieces. That's going to be 2x if the quantity 2x is greater than or equal to 0, and it's going to be equal to -2x if that quantity 2x is less than 0. Now remember, we also had the division by x, which was at 0 was equal to 0. So we are dividing both of these as we're writing this as a piecewise function. We are dividing each of the pieces by x here too. And so what ends up happening there is that the absolute value of 2x divided by x, as soon as I divide by x right here, I can no longer have this equal 0. I lose the ability to equal 0. This function is not defined when x equals 0. So we have to take that out of the domain. So this is going to be equal to, and I'm going to simplify a little bit here too, 2x divided by x is simply 2 if x is greater than 0. Well, what did I do there? I also divided both sides here. I simplified the statement on the restriction there. So I divided both sides there by 2. Okay? So I divided, that's what I'm doing there. And -2x divided by x is going to be -2 if, and again, same thing, I'm going to do a quick little division here just to simplify that statement so that that's true if x equals 0. And note that the absolute value of 2x over x is undefined when x equals 0, right? This function is not defined when x equals 0. Okay, so there was how I'm going to actually take that function and write it in pieces. So here is writing, let's write it this way. This is creating the piecewise function. Or rewriting is maybe a better way to say it, right? We're just taking what was given in its absolute value notation and we're breaking it down and writing it, creating that piecewise function that corresponds to the absolute value of 2x over x. Okay, so what does that mean? If that's the function that we're working with and we want to take the limit of that function, so let's go back to taking the limit. So we're looking for the limit of the absolute value of 2x over x, which we were already tried some direct substitution and realized it gave us that 0 over 0. So now let's get in and let's actually take a look at it. Notice non-directional, which means we must consider both sides. So we must consider both x approaching 0 from the left and x approaching 0 from the right. Anytime we have a non-directional limit like that, we need to consider both the left and the right. Okay, so let's do it. So what is the limit of the absolute value of 2x over x as x approaches 0 from the left? Let's do the left first. So working from the left, as we're coming from the left of 0, that is, right, if we think about 0, coming from the left of 0, coming this direction, if this is our x's, coming from the left of 0, those are the values of x that are less than 0. So coming from the left, this, go to our little piecewise breakdown over here, this is the function that we'd be looking at. So coming from the left, we're plugging in numbers like negative 0.001, right? And that is definitely less than 0. The value of this function coming from the left of 0 is going to be negative 2. So this is equal to negative 2 coming from the left. Okay? So we're looking over here at the piecewise function. We're utilizing this function that we just talked about, that we just wrote. We're coming from the left. So we're saying, well, if we're coming from the left, it's actually just that constant function, right? It's simply negative 2, the function's value for all values of x less than 0. This particular function has a value of just negative 2. So that's a negative 2. Coming from the right, so now let's look at the right. Coming from the right, so if we take the limit as x approaches 0 from the right of the absolute value of 2x over x, well, coming from the right, as we come from the right, so again, think of this as your x and your zeros, and we're coming from the right. That's the values, looking at our piecewise function, that's those values where x is greater than 0. So this is the coming from the right of 0. This is the part of the piecewise function that we're going, or the piece, I guess I should say, of the piecewise function that we're going to use if the values of x are greater than 0, which they will be as we come to 0 from the right. So coming to 0 from the right, look over at your piecewise function. The output, the values of the function are always just 2. So this is going to be 2. And we can see right here that we have an issue, that the left and the right-hand limits, guess what? Not the same. Okay? If this had been a directional limit we were looking at, we would be able to say what the limit is from the left or from the right, but the fact of the matter is they do not equal. So our answer here, the limit as x approaches 0, just 0, non-directional, of this piecewise function, even though it doesn't necessarily look piecewise, it is an absolute value as a piecewise function, does not exist because, and we've showed right above, why not? But now I'm going to justify it in my answer statement, because the left and the right-hand limit are not equal. And we've shown that right above. Now, we could also graph this particular function, and we've got that piecewise function, so I'm going to just squeeze in the graph so that we can have a visual here too. The graph of this function, if we were to want to have graphed it, and I didn't do the graph first, I wanted to do it without the graph, but we have the graph and it would be easy to do, or we have the piecewise function definition and it would be very simple graph to plot. So if the x's are greater than 0, this function is the constant function 2. Okay? Now remember, right at 0 it's undefined, so I have to put a hole there, but it is just 2. It's 1 and 2. So for all values of x greater than 0, the output value is just 2. And for all values of x less than 0, so to the left of 0, the output value of this function is negative 2. And so we have this graph right here. And so you can see right there, obviously the right-hand limit, coming into 0 as the x's march towards 0, our graphical, just a review of graphical limits. You can see that that limit would be positive 2, and marching your x values in towards 0 from the left, you can see that your limit value would be negative 2. And those clearly do not meet. Those two limits are not the same. The left and the right hand are not the same. So here's a nice little graphical explanation of why those limits are not the same too. So we can see it graphically, we can see it with the function. And we even got a little review with absolute value and writing absolute value as a piecewise function, which is something that we do frequently when we need to think about absolute values within functions. It is often useful to break them down into their two pieces when the argument is positive and when the argument is negative.